And the next one is the accuracy of vectors include this objective features. This obviously by V.
Hello everyone, my name is Yu Qiao. I'm from the Shenzhen Institute of Advanced Technology, Qianjin Clinical Science. And this is a joint work with three of my students, Peng Xiaojiang, Huang Yiming, and Cai Zhongwei. And first I would like to introduce our institute because it's a relatively new institute. It was established in 2006 and by Qianjin Academy of Science, Qianjin University of Hong Kong, and the Shenzhen City University, the Shenzhen City government. And actually, we already have 2,000 employed students, and it's not developed very fast in the last years. And our computer vision and pathogenic research group started from 2009. And in the same year, we work on IP recognition. And in the same year, we use the database developed by UCF till now. So I appreciate the database you provided. It's very important for this society. And in this case, we have 3 first author papers. CRCV this year. And this is the location of Shenzhen is very near Hong Kong, so next time if you come to Hong Kong, maybe you can give us a job. From Hong Kong public sector, it takes about 1.5 or 12 such as right, and that is a full-time institute. Okay? So here is the outline of my topic in 2 parts. First is our principle of UCF 101. Actually, I will talk about several engineering things on how to make a good performance on this data set. I think with this engineering, it is a tricky thing. You can easily get more than 87% recognition accuracy on this data set. Not so difficult. I think after you heard this talk, you can ask your student, maybe you take 1 day or something, you can implement all the research. That's all. And the second thing is we will talk about some other middle level and semantic-based representation for video activity recognition, which we believe is the future of this field. And especially I will talk 2 papers, one is Lecure this year, they are with CRCV this year. Okay. I think here, everyone be familiar with this technical pipeline object recognition. Further, we have videos, we try to locate these characters, and the trend dictionary. Then we use this dictionary to encode this paragraph from the import video, and then we deploy it on production and do the implementation. Actually, for each step, we have a couple choice. We'll talk about this type of interpreter. And for the trending dictionary, we have k-mean, we have sparse coding, we have GNM, and for encoding, we have recursive of the assignment, sparse coding, and LRC, which are very good narrative. And also for we have semantic one to another. So what's the best combination of server for UCF 101? This is the question I'm going to answer in the next few minutes. So it's pretty. And okay, for detector, the most typical STH and density trajectory, I think we all know this trajectory give better performance. And also for this describer, we have how MPH. Among these MPH give the best performance, and if you combine them all, you have wonderful performance. So science is very critical on this. Just skip, just want to say, density trajectory for us, how MPH is a very good choice for this task. The first thing I want to say is the pre-processing of the describer is very important. Here I show you some results. You can see, we just do a sample PC and plus Python pre-processing. We have the solid line, which is the mercer use PC and plus Python. And we have also the dashed line, it does not use PC and Python. It does not use PC and Python processing. And the different color means different encoding mercer, which actually has 3. Feature vector and LRC also we carry this. For all the mercer, PC plus Python have significantly improved performance. Okay, so let's do. I think I noticed many teams use PC, but not many teams do Python, and this also can improve. Compared to use PC only, PC plus Python can improve the performance further.
So why did you just remove the
Right. Yes. I think it's important because for some dimension of the PC initial detection, the words are very small, and it makes the geometry of K-means unstable. I believe there may be some better transformation than this morsel, but on table choice, it's a good choice. Okay. The second thing I want to say, the encoding or server, we have noticed many teams use the feature writer and VRAD. Yes, they're very effective. Actually, we noticed this actually at the 2011. We actually have a paper in 2012. I think it's the first paper which applied feature writer on action recognition. For this table, we only use this. Because this paper was 2 years earlier.
So you can combine both.
Finally, in this paper, in this talk, I will come out.
It's interesting because VLAD is a simplified version.
Yeah, I will talk the relation later. So relation is not good. And first, I have some comment on feature writer. Feature writer, you know, is defined with the feature kernel and the derivative of the parameter of the universal GNM manifolder at the given set of the descriptors. Actually, in my view, feature writer is very related with the GMF adapted supervisor, which has been long popular used in speaker conditions. Some of you know. You know, this like this. We have a universal background GMF like this, and we have some new point here. And in the GMF adaptation, we adapted this kind of GM according to a new input data. Okay, what the feature writer capture is actually the difference between the two GMF, which means this circle, this solid circle, circle, and this dash circle. For example, if you only consider mean, it's like this writer, like this red lines. But for in speaker recognition, for GMM adapted supervisor, it only use the absolute operation, not the relative operation, with GMM syntax. Actually, a few years ago, we have a paper. We write a manuscript on GMM adapted supervisor was actually recognition. But unfortunately, this paper was rejected a few times, and later we realized some other part of the feature writer and they are this idea. I just want to emphasize the performance of feature writer and GMF adapted feature writer is very similar. And it's the key idea. Also, it's developed in different level. The key idea is near. Okay, the another thing I want to say is about VRAD. Also, VRAD just as you cited, the condition as a hard version of feature writer, which use the K-mean to replace GMM, and also it originates the mean difference of each cluster. And we also try another VRAD to solve the VRAD, which means that it still use the K-mean to learn dictionary. But for each local describer, it's associated with K. More than 1 year is a cluster. So for each describer, they can work for multiple clusters. And just given by this equation, it's similar to solve the segment for the Lecure server. And maybe so you want to know which is better, so we have that information. Here, this means the number of the cluster we used in the side, and this is the recognition accuracy. Actually, you can see for the if the cluster number is not so large, if the number of cluster or the size of dictionary is not so large, and the traditional VRAD gives better performance. But if the cluster if the size of dictionary is larger, and the soft VRAD can improve the recognition rate a few bits. This is because if you have very large code book and if you only select one, it is one. Maybe there are the multiple words which can be near to the input descriptors. So the final thing I want to say is about normalization of feature writer and VRAD. Actually, we use the 3 normalization. One is the power normalization. We also know that some teams use this. It's just root normalization and this equation. And another one is the R2 normalization given by this equation. One thing is different between our approach and others is we also try intra-normalization. That's we normalize the vector according to each input component, which means according to each Gaussian or each K-mean cluster. And we notice this can also improve performance. So here you can see the results. We find for both feature writer and VRED, the root power normalization plus L4 plus normalization to the better performance. And also, the second one is given by power R2, which is widely used by most of widely used by many teams in these times. But if you use normalization, you get this equation that can be more. So here, finally, we find that just very linear thing. We can combine feature vector and solve VRED. And this also can lead to some improvements. Also, but not so much. And this gave our system for this challenge. I mean, because we have very short time to take part in this challenge, just after your deadline, we use 3 or 4 days on this task. The students are very tired of combining a single interface. So we did not do everything what we want to do. Actually, we originally want to do something later. We try to do some mid-level symmetric representation for this task. And we want, just as mentioned by Dr. Liu Jingzhen, and we made some mistake on our submission for this result. We just mistake between the index of these two pair of classification, which lead to that's why the recorded result is lower than the corrected result. Our corrected result should 87%. Okay, I think that this come to the first part of my talk. And the second part is we want to talk about several semantic and middle-level representation we developed for IC rationalization. The first one is the motion light. Actually, in this work, we try to find some special temporal parts for IC representation. The second is we try to mine some useful temporal structure for part-based classification. Our motivation is like this. You know, when we first write a relation, we first see which cycle more served in the image field. We're talking about human detection part method. So what we said, how does this mean? I think we can learn 2 things from this kind of approach. The first is it divides the complex application into relatively simple parts. That's what we want to do for two. The second is it model, we do develop model, the model structure between different parts. And these are 2 things we want to also generate for action. So what are good part for the relationship so that the action? I think we have three properties. Before I think it's repeatability, because this kind of part can repeatedly appear in different type of actions and also in different videos. Second is reproducibility, because we can use this kind of part to find different kind of videos and different kind of actions. The last is has this quantitative ability for classification. So then we have 3 questions to solve how to find our use. Actually, we have 2 parts here. One is the motion light. The motion light in this part, we only try to find the special temporal parts. And then in the second part, we only find the temporal part, but we mine the temporal structure part, which means we use different parts, we call motion grid, which is the classification. We also notice there are some similar papers, similar here, our paper, the ICCV is here, which is very similar to motion light. Okay, when we do motion light, what we see is like this, you know. In actual generation, there are at that time there are 2 popular parts. One use local descriptor, and just I talked in the first part of this speech, how MDH and then use DOW feature writer summarize this kind of descriptor for representation. The other work in treating the action bug, you know, it does not use local feature, it uses some video volumes as action bug and some global template, which is called template for representation. What we think is the local driver and the size is too small to have to put the local and repeatability. This practice is limited. One action bug has to share the local and this practice but it cannot be repeated well by different actions. So what we come to do is we just try to make balance between the local features and the high-level implementations that we do with motion light. We can share the both advantages, low-level and high-level features, and have a good repeatability from the case. What we did is actually very simple. We first find some motion silence regions. When we cluster the silence regions into some candidates for motion light, and then we define, and then we use some similarity function to cluster the candidate motion light, and then we use some descriptive and repetitive measure and to make a run and select the motion light within the field for regeneration. And the brief, and I do not have time to do the detail, but I can show you some motion light that I find from different data sets from KTH, from UCF, and from HMDB. What we found is for simple database like KTH and Vigma, this kind of mercer can really define some more meaningful and repeat the lights. But for UCF, Vigma, and HMDB, for light data like this, it can define something meaningful, but something not so meaningful. It cannot be related to interaction. I think this probably is so in the future.
So these are what we have special technical agents which have silencing, like what?
Yes, we support the HOE to distinct among the silence of motion. And with this silence light, we can find the generation also in a big volume for some qubit. And we try to qubit as a candidate for motion lights. Then we distinct the similarity between different motion qubits and two clusters. And we use the cluster center as a candidate for motion lights. And then we run. We just, because there will be a very large size of the candidate at this time, some does not relate to any issues. So we run according and select according to their repeat parameter.
So this special sample regions is of the same size, same number of
different size. That's a very good question. That's a clever keeping so that different size. First, I think for two qubits with very different size, we just different motion light because we want the motion light with different scale. But for motion light with similar size, we just match it like this. We just find the overlap which gives the best similarity, which gives the best similarity.
So is it like, it is like a superpower, or what's the between this and the superpower?
Yeah, it's related. Basically, it's similar, but it's technically in a different way. Because for supervisor, we do segmentation on the right here. Okay, anyway, our results like this. First, for our ranking mercer, because we saw the ranking and select mercer, they can give better mercer. This blue line we use all the time. Actually, its performance is even worse than use part. And this black line is random selection. For both HMDB and CRCV and our selection mercer performance. The second thing we want to say is if we combine the motion light with low-level features, we can get further improvement. That's actually what we wanted did for UCF 101, but we do not have time to do it at that time. We try to combine the middle-level implementation with the low-level implementation. We believe it can further improvement for storage. Because I'm calling offering for KTH for UCF 51 for UCF 50. We already showed the improvement. Combine the middle implementation with the implementation. Okay, the second thing is we try to just set the structure between different parts, between parts. So we combine the motion item into three. I'm also running motion all the time to our package. And we further determine the motion item and this motion environment. And we convert motion item into an all structure. So all structure, all the translation of motion item to deal with the time of operation. And the end operation try to combine the sequence of motion items. Also, we develop some manual to find the motion free with the combination of several motion outcomes. Here are some examples we find from the oriented data side. And I think it's very similar to human perception of this kind of spots. For example, the diagonal spots will find standing will lead to one motion term, and the jumping will lead to another motion term. This is for the non-jump, and the breaker for jump will lead to one step, and the jump in the air to another motion terms. Okay, also we find that use the motion term and motion free can improve the performance compared with the motion term. Okay, here is the summary. First, I talked about the currents maybe you want to know. I have detail into our purpose, but it's very linear, but I think it's helpful for you to improve performance. And the second thing is we'll talk about some ongoing work. We try to develop some semantic and verification implementation for actually video. Actually, we want to do this for live skill data set, like we said, one. Also, I think the most actually detection that we are treating problem also the kind of application. This work is dealing with students here, photos, some here. Also, we also have some detection results so we can show. This IMSR data set is relatively simple compared to CRCV, and this different color mean different part of the motion. We try to detect from the video. In this case, we consider both the time promotion part feature of each part and the relationship between different parts. For example, if we detect a hand waving, this kind of walking actually will be ignored by our detectors. Below in our some templates that are not shown. So, thank you.
Time for questions? One last. Understand how you measure the similarity of your motion. Once you detect the areas, how do you understand it?
You know, we have category label, action category label for each video, right? And we count whether this kind of motion outcome or motion type exists in certain category of videos and use this. For each video, we do the motion light or motion outcome type. And with the response story, the type which needs this kind of video to do it. Then we can find whether a motion light or motion outcome is associated with certain motion action category and use this to so you can find it in definition. Yes, probably you can think of motion action or motion light or motion outcome as a category.